Hello viewers, this is the automated window shutter project and it is sponsored by the Ideal Plantation Shutters Company. My name is Binoy and our team consists of myself, Francisco, Abdu and Asif. Here I'll talk about the two popular options for window shutters based on the type of louver. Uh, a louver is the horizontal fin on the shutters that rotates to open or close. Shutters with thin and short louvers like the one you see on the left. These are what most of us have in our homes and they're commonly known as window blinds. Then there are the shutters with thicker and wider louvers and these are known as plantation shutters, as you can see on the right. Plantation shutters have the following advantages over window blinds. For example, they are better at insulating homes. They're easier to maintain, and one of the biggest advantages, they can last much longer than traditional shutters. However, their design also makes it harder to control, and when you have multiple shutters controlling, all of them becomes a very tedious task for the user. Automating plantation shutters would therefore help tackle this problem and help make it a more popular alternative for people. Unfortunately, there aren't many automated multi-plantation shutter options in the market. Of the few that are there, they're quite expensive with the cheapest option starting at $150. So this is where the window shutter project comes in. Our project aims at designing an automated window shutter solution to controlling individual and multiple shutters. The shutter is motorized and can be controlled manually, automatically, and wirelessly. All this is done while keeping the production cost low to about $20. So for our projects, we have the following requirements. Some of the important ones, including battery life, um, keeping this module running for at least 6 months, and also designing this module within a $20 budget. One of the constraints that we face is the shutter frame dimension. The module can only be placed behind the fixed bottom louver of the shutter, which has a width of 82 millimeters. Also, the maximum height of a component that can be placed behind this louver is 24 millimeters. So we had to work within this size when we were designing our shutter module. Only the length of the bottom louver was not a constraint, as this depended on the length of the window where the shutter was going to be placed. But for most purposes, the length was not a problem. The other constraint was the prototype shutter. The prototype we were given did not exactly match the actual window shutter in terms of louver length and number of louvers, and hence our tests and design for the module had to be modified to take into account these differences. Also, since we had only one prototype, we had to take extra care to do tests without damaging the frame. Now here's a general overview of the window project system. So our window shutter design consists of three components: a motorized shutter, a phone application, a hub, and a hub that acts as a gateway between the app and the shutters. Now, since Wi-Fi allows long-distance communication, the hub and the phone are both connected to a common building Wi-Fi and communicates between each other through Wi-Fi. This gives the user a lot more operational range in which they can control the shutters. Now, however, to save power for the window shutters, the hub communicates to the shutters through Bluetooth Low Energy. The hub is capable of connecting and managing multiple shutters within a radius of 50 meters. The user sends shutter control commands from their phone through the app, which is first sent to the hub and then sent to the shutters.
Here's the previous design that was given to us for the shutter system. It had one too many components and involved soldering and printing PCBs. Relative to that, here's the block diagram for our revised window shutter design. This highlights the major components and the types of connections between them. Highlighted here in red is power, blue color is signal, and in black color we have mechanical connections. As can be seen, this design is a lot more efficient. It uses less components and removes the need of printing PCBs, as all the components seamlessly integrate in terms of voltage and current. In this design, we have a portable battery that supplies 5 volts at 500 milliamperes to the ESP32. The motor is given 5 volts at around 300 milliamperes by the ESP32 and is controlled by a pulse width modulated signal from the ESP. The servo is connected to the louver through a shaft and a pulley mechanism, which is also discussed in the later slides. Um, The hub communicates with the mobile app through Wi-Fi, and it communicates with the ESP32 via Bluetooth. The test results that we made showed that the test results that we did showed that the ESP32 required a 20,000 milliamp hour power bank to last for 6 months before charging it again. We chose a rechargeable battery pack that connects directly to the ESP32 through a micro USB cable. The USB connection allows the user to easily remove the battery for recharging after 6 months. The dimensions of the battery pack is 6.5 inches by 3.1 inches, which fits behind the bottom louver. The ESP32 Dev Kit C module, which we are going to be using, comes with an entire small size system on chip, which in terms of current and voltage seamlessly integrates with our motor and battery choice. This was an important constraint that needed to be considered in our design, as not a lot of space is available behind the bottom louver where this is going to be installed. Most of the I/O pins are broken out to the pin headers on both sides for easy interfacing. It is possible to connect peripherals with jumper wires or even mount the whole entire chip on a breadboard. Inside the ESP32 chip is a dual-core 32-bit microprocessor along with 448 kilobytes of ROM, 520 KB of SRAM, and 4 megabytes of flash memory. It also contains a Bluetooth module, a hardware accelerator module, an RTC module, and a lot of other peripherals. It offers a low-power deep sleep mode, which we'll be utilizing in our application. This is possible because inside the RTC module there is a small 32-bit ultra-low power coprocessor (ULP) and 8 kilobytes of RAM memory which stays on during deep sleep. The Bluetooth radio and baseband on the ESP32 support Class 1, Class 2, and Class 3 transmit output powers and a dynamic control range of up to 100 meters in an open field. We will be utilizing this Bluetooth module for BLE communication with the hub. However, the dynamic range we used was 50 meters on our ESP in order to conserve battery. This was more than enough as the requirement was only about 30 meters of range.
Our design consists of a new motor, which is a servo motor SG5010. It operates at a voltage ranging from 4.8 to 6.6 volts, having a stop torque of 6.5 Newton cm. It meets our minimum torque requirement of 5.7 Newton cm. The gear type is carbon fiber, and it has a rotation degree of 180 degrees in both directions. The gears of this motor had enough friction to keep the louvers at its last position, even when it's not powered. The servo motor has an internal rotary sensor that keeps track of its louver position. Our design also includes a push button that will allow the user to open and close the shutters manually. In this case, when the user does not have the cell phone close by and when the user wants to only send a simple command like open and close, they can just push the button on the shutter and each push toggles the command between open and close. The dimensions of the breadboard was modified by splitting into 2 halves along its length. This allows us to securely connect the ESP32 and use its other pins if needed in the future. The wires from the servo motor and push button were crimped to fit the wires tightly into the breadboard holes, thus keeping the connection intact. The dimensions of the small breadboard is 82 millimeters by 50 millimeters. These pictures illustrate the servo motor assembly connection drawings. The servo motor is 1 3/8 inch by 1 5/8 inch. This motor will be placed behind the bottom fixed louver with the motor shaft facing to the right. Then a 1-inch long shaft attachment will be connected to the servo motor, and that will connect to the first pulley. The belt will connect to the second pulley that is connected to the louver shaft. For this servo motor, it will have a small shaft connected to the first pulley, then a second pulley will connect to the window shutter louver. The length of the belt is 7.88 inches and has a width of 0.25 inches that will connect to both pulleys. To ensure that there is no slippage, it is extremely important to have a tight belt that fits on the grooves of the pulley. That's why we added the rectangular 4 3/4 inch PVC to be screwed into the pulleys to keep a good separation and to keep the belt firm. The dimensions of the prototype shutter frame given us were approved by our sponsor. The difference between the prototype and the actual shutter would be the number of louvers and the louver length. Other measurements are the same on both. Here on the right side table, you can see all the components are numbered and named. This is the wiring diagram of our shutter module, and it shows all of the components inside. The red wire represents the connected to the 5-volt pin, the brown wire represents connected to the ground, and finally the yellow pin represents the wires connected to the I/O pin to transmit the signal current. The overall system setup consists of a 20,000 milliamp hour portable charger and modified breadboard, ESP32, a development board, a push button, a shaft, 2 pulleys with the belt. All of the components are designed to fit behind the bottom louver of the window shutter. A shutter cover and a battery holder models were 3D modeled on Fusion 360 and converted to a 3D printable STL files. The size and constraints of the bottom louver was kept in mind while choosing the dimensions of the cover and the holder. They were both designed having a minimum 2 mm thickness.
For the hub design, the Raspberry Pi Zero was ideal as it comes in with a built-in Bluetooth module which is required to communicate with our Shutter ESP32 modules. It is already FCC certified and comes in a small case. All of these are extra costs which our sponsor does not have to care about anymore because it's already there. Hence, it was a perfect option for us. It consists also of a Wi-Fi module, and through it can utilize its IP to find its location and access sunset and sunrise times, which all come in handy for features in our product. It also receives HTTP requests through the app via the network router locally and stores these requests and schedules in a file directly in the directory in the Pi memory. These HTTP requests also trigger the Pi to send Bluetooth commands to our Shutter module, and the Pi also sends meaningful ASCII characters, which is received by the ESP32 over Bluetooth. These characters are predefined in the code where upon received, they perform tasks like open or close the shutter or move them to a certain angle. The BLE or Bluetooth Low Energy parameters that this hub uses are the same as the ESP32, and we're going to talk more about that in the next slide. The Raspberry Pi also acts as a local cloud where it publishes its IP, and anyone connected to the same network with the app can access it and use it to share information. The Pi also can connect to multiple Shutter modules at once and control them. It differentiates between each Shutter modules using the individual or unique MAC addresses that the Shutter modules have. BLE or Bluetooth Low Energy is a power-conserving variant of Bluetooth. BLE's primary application is short-distance transmission of small amounts of data at a lower bandwidth. Unlike Bluetooth that is always on, BLE remains in sleep mode constantly except for when a connection is initiated. This makes it consume very low power. BLE consumes approximately 100 times less power than Bluetooth, depending on the use. Additionally, BLE supports not only point-to-point communication, but also broadcast mode, where the server transmits data to many clients that are connected to it. They both have the ability of transmitting up to 100 milliwatts of power, or the range of a Class 1 Bluetooth module. Due to its properties, BLE is suitable for applications that need to exchange small amounts of data periodically running on batteries or low power applications like ours. With Bluetooth Low Energy, there are 2 types of devices, the server and the client. The ESP32 can act either as a client or as a server. In our case, we use it as a server. The server advertises its existence so it can be found by other devices and contains the data that the client can read. The client scans the nearby devices, and when it finds the server it's looking for, it establishes a connection. BLE works using GAP and GATT protocols. GAP is basically used while the device is advertising for a connection. This tells us about data like signal strength and the flags in the local device name, etc. GATT, on the other hand, defines the way that 2 Bluetooth Low Energy devices transfer data back and forth using concepts called services and characteristics. makes use of a generic data protocol called Attribute Protocol, or ATT, which is used to store services and characteristics and other related data. All this is stored in a simple 16-bit lookup table, with 16-bit IDs for each entry. The top level of the hierarchy is a profile, as shown here, which is composed of one or more services. Usually, a BLE device contains more than one characteristic, or also reference other services within the service. A service is simply a collection of information like sensor readings or simple ASCII character messages in our case. The characteristic is always owned by a service, and it is where the actual data is contained in the hierarchy. The characteristic always has two attributes, the declaration and the value. Additionally, the characteristic value can be followed by descriptors, which further expand on the metadata contained within it. These properties describe how the characteristic value can be interacted with each other. Um, A few operations and procedures that can be used with the characteristic are read, write, or notify, etc. Each service characteristic has a each service characteristic and descriptor all have unique UUIDs, or universally unique identifiers, which is a 128-bit number, and an example of this is shown here on the screen. So our hub is the translating agent between the mobile application and the smart shutter. It handles requests sent by the mobile application and sends BLE commands to the smart shutter using the local network it is connected to. It communicates to the app via HTTP requests that include registering new shutters, creating groups, adjusting the position of shutters, and scheduling both groups and shutters, as well as changing the mode of a group or shutter. To connect and to talk to the smart shutters, libraries like BluePy were used that support BLE. The hub also needed to retain all the previous settings set by the user through the app, even after the user's phone has been turned off and no longer in use. The hub will always be on to process all the scheduled positions for the groups and shutter, which would be defined by the user and handled by the background scheduler called an APA scheduler. On the right, it is shown that shutter 1 and shutter 2 have been scheduled to certain degrees at certain times, and the way the scheduler works is as it arrives to the set time, it will send the set degree values to the specific shutter that has been scheduled for that time. Another feature we have in our design is the opening and closing of the shutters at sunrise and sunset times. This feature was made possible due to the IP Info API and the Sunset and Sunrise API. In order to get the sunset and sunrise times, we get the latitude, the longitude, and the time zone the shutter is in. These were obtained by accessing the IP Info's database, the IP API's database, which maps the location information based on the IP addresses. We chose this solution due to the hub's inability to get its current coordinates without having an external GPS module. The location variables were then used to receive the sunset and sunrise times, and these times were also updated at 12 a.m. automatically using the APA scheduler. Lastly, for the grouping hierarchy, due to the smart shutters being developed for nursing homes and general housing, a multi-level grouping provides a type of hierarchy among the groups in the configuration shown here. For example, sending an angle adjustment command to the top floor group will result in all the shutters in the subgroups to adjust as well. Also, any mode set to an upper level group will supersede the modes of lower level groups and shutters. This is a demonstration of an application of this project where more than one hub is required. The Bluetooth range on each shutter module or ESP32 microcontroller was set to 50 meters. Therefore, the hub has to be within 50 meters of each individual shutter module it is connected to. If the range exceeds the 50 meters, two hubs will be used as shown in the figures. Both hubs will have to be registered to the same Wi-Fi network through the application. With regards to the ESP32 for our design application, we will be utilizing the Bluetooth module, the core and memory, along with RTC memory and RTC peripherals, and most importantly, the ULP processor, which is the only processor that works in deep sleep mode. The ESP32 comes with 5 configurable modes, but we're only going to be focusing on the active mode and the deep sleep mode. We'll be working with deep sleep mode in order to get the most efficient battery life in our design. In this mode, power is shut off to the entire chip except RTC module, so any data that is not in the RTC recovery memory is lost, and the chip will thus restart with a reset. This means program execution starts from the beginning once again. So unlike other sleep modes, the system cannot go into deep sleep mode automatically. So special functions can be used to immediately enter deep sleep mode um, as long as the wake-up sources are configured, which we did using code. Additionally, it is possible to individually code what peripherals need to be shut down or kept on before entering deep sleep mode. However, by default, ESP32 automatically powers down the peripherals not needed by the wake-up source. All of this is very useful in our application. For the development of the mobile application, React Native was used as a framework of JavaScript to develop a cross-platform app which would work both on iOS and Android. CSS was also used for a more user-friendly experience. Suggestions for the hub were parsed to append and then display on the mobile application. The user starts by having 4 options as shown here on the screen, on the home screen of the app. The options are to scan the shutter, to view the groups, to scan hubs, and to connect the hub to the local Wi-Fi network. Once a shutter module is registered, its angle can be controlled using a horizontal bar as shown here. The user can slide to a desired angle and set the shutter position. The graphic on the screen shows the present position of the shutter. It also has a scheduler and a local weather and time widget, and a complete demonstration of the working of this app is shown in the upcoming demo video.
As mentioned earlier, the smart breadboard was modified to fit the ESP32 board on it. The servo motor terminal pin was removed and crimped to the corresponding breadboard holes. The push button wires have been crimped and connected to the breadboard. Having all the wires crimped ensures that no connections become loose in the circuit. For the fabrication of the mechanical connection, the first part was to make a hole where the motor shaft attachment would go through and connect to inside the first pulley. Then we used a 3M double-sided foam tape to attach the servo motor in place. The rubber teeth belt is secured between the teeth of the 2 pulleys. The last part was to add the rectangular PVC that would be screwed into the pulleys to keep a good separation and firm belt. The connection of the push button is between the 5-volt pin and pin 33 of the ESP32. The fabrication of the push button involved carefully drilling a hole on the bottom louver and fastening the button in place using a nut and a washer. These 2 images show the front view and back view of the push button. The fabrication of the shutter module cover was to have a final product that is professional. The shutter module cover will hide all the wires and look more appealing as a finished product. The images on the right show the shutter module cover on the window shutter prototype. Since our prototype window shutter uses a portable battery pack that needs to stay behind the bottom louver, a battery holder was 3D printed. The holder allows the user to effortlessly slide in and out of the battery pack. The dimensions of the holder fits well behind the bottom louver and keeps the battery securely in place.
All right, so coming to testing, one of the tests that we've done is the torque test. Our module was required to handle torque, which was 10 times the minimum torque required to move the prototype louver. We conducted torque tests on our prototype shutter, and the torque came out to be 0.57 Newton centimeters, which meant we needed a module that could handle a torque of at least 5.7 Newton centimeters. The servo motor we chose had a torque of 6.5 Newton centimeters, therefore meeting the torque requirement. The next test we did was the power test. We basically tested the current consumption of our module, and we did this for all possible scenarios that we felt the window shutter would operate in. All these current readings were recorded, as you can see here. Here you can see the results of our current tests and power calculations. For this calculation, we made the assumption that the shutter would be used on average only 6 times a day, and that the motor movement for every command would last an average of 1 second. The total power consumption in 6 months came to about 16,000 milliampere hour, which means with our 20,000 milliampere hour battery, our shutter can last for 7 months. We tested the shutter's Bluetooth range for the Bluetooth range test. We did this by increasing the distance between our phone and the shutter until the Bluetooth connection between them was lost, which indicated that it was out of range. We did this test a couple of times indoors and outdoors and noticed that when the two devices were directly in line of sight, it was able to operate easily at a range of up to 40 meters, and in some cases even a bit above 45 meters. Here in this video, we see Asif able to successfully send a BLE command from his phone to the shutter. He did this from a distance of about 35 meters. Coming to the production cost, our module design costs only $13.57 when bought in bulk from international vendors. This was well under our $20 budget. In conclusion, we designed a shutter module that is able to effortlessly move the louvers in order to open or close the shutters when needed by the user. The module was efficiently designed in order to minimize the number of parts involved. A battery life of up to 7 months was achieved on the module. Also, a hub was designed which seamlessly combined the use of BLE and Wi-Fi signals for efficient communication between both user and shutters. Lastly, a multi-platform mobile application was successfully developed and integrated with the design. All of this was achieved within our designated budget. Okay, here's a quick demo video we put together demonstrating our project. Just want to note that in our demo video, the button is loosely attached to the shutter board, but this is not the final product. The final product had the button attached, as we have seen in previous slides. Also, since we were limited with one prototype shutter, we used a dummy shutter to illustrate multiple shutter control. The dummy shutter is different from a prototype shutter only in that the microcontroller controls an LED instead of a servo. Otherwise, it functions the same way. So here's the demo video.
Motorized window shutter for medical institution and retirement home use. The window shutter project uses 3 products: a phone application, a motorized shutter, and a hub that acts as the gateway between our app and the shutters. We also use a dummy shutter here for demonstration purposes. Let us see the several ways a user can control the shutters. Real-time control via app. After opening the app, the user first scans for shutters. Here, we have 2 shutters, the prototype shutter that we built, and a dummy shutter that switches an LED on and off. The phone communicates over Wi-Fi, first with the hub, and the hub in turn communicates with the shutters through Bluetooth. When the user finds the first device, he adds it to a group which he names University, and he names the device LED. He then finds the next device, which is a prototype, and he names it Shutter. Then he adds it to the existing group, which is University. When we go back, we can see the group and the added devices in the group. Now the user can control the whole group, which controls both devices simultaneously. Therefore, when the user sets it to 90 degrees, the shutter moves 90 degrees and the LED on the dummy shutter lights up, indicating that it has also moved 90 degrees. Now, when it is set to a different angle, the louver on the first shutter moves to that angle and the LED on the other shutter turns off. The shutters can also be controlled individually. Here, when the user sets the dummy shutter to 90 degrees, the LED lights up and then turns back off when set to another angle. As you can see, the prototype shutter has not changed its position. Pre-programmed control via app. You could also set a time when you would like the shutter to move. Here, the user schedules the shutter to move to 180 degrees, and he sets the time as 12:11. As it can be seen, when it becomes 12:11, the shutter moves. Another useful feature that our shutter provides is the sunrise-sunset schedule. This schedules the individual shutters or group to open at sunrise and to close at sunset. If connected to the internet, it even keeps track of the changing sunrise and sunset hours. This feature, along with the grouping feature, would be useful in places like hospitals and old age homes where the staff can deal with hundreds of shutters in hard to reach places, and that too on a daily basis. Manual control via button press. If you don't want to use your phone, or if you don't have your phone near you, you can still control the shutter manually using its inbuilt button. Each press simply switches the shutter between open and close. Our shutter is battery powered and it can last about 7 months. It gives 3 different modes of control and has a Bluetooth range of 50 meters. Our team aimed to create a robust and suitable solution to the multiple window shutter problem. And this is our solution.
Moving forward, here are a few things to be considered before going into production. Although the ESP32 has sleep modes which allow it to save power, it is not really as efficient as we expected it to be. Here are 2 other alternatives that were considered for a much better battery life. Here, our first solution, we talk about the Pro Mini alternative. Now, this solution was much more efficient in terms of battery, but the catch was that it wasn't a single chip solution. It used a Bluetooth module and a microcontroller on 2 separate chips. So these needed to be soldered together, and we would have to eventually print out a PCB. But as you can see, the solution has a much better battery life. It only uses 712 milliamp hours in 6 months compared to the 16,000 on our ESP32. Here is another solution, which is the Blue NRG solution. This is an entire single chip which has the Bluetooth module on the chip, and it also is a lot more efficient. But the thing is, the voltages our motor uses and this chip uses are different. So you would still end up needing to have a buck or boost converter and eventually have to print out a PCB as well. But as you can see, the theoretical values for this are a lot less than the 16,000 compared to our ESP32.
Finally, here are some other things to be considered by our sponsor that would improve the quality of the product. We could replace our current power bank for a solar power bank that would even further improve the battery life. Furthermore, an integration of the web service like AWS would allow the user to communicate with the shutters even without being connected with the same Wi-Fi network. Lastly, another neat thing to have would be the ability to integrate a voice assistant like Amazon Alexa to allow the user to control the shutters through the voice commands.
All right. So we would like to thank our sponsor, Mr. Frank, for giving us this opportunity to learn and to do this project. We would also like to thank Freddie and Shashir, who made all the CSE side of the project possible and endured the long, hard meetings with our team to help us integrate their design with ours. Finally, we would also like to sincerely thank Dr. Kondraske for his guidance and support throughout our project.